All right, silly people, here's the situation. Uh, we're going to be finding the expectation values of momentum position, um, position squared and momentum squared of general wave function psi n, right? Um, and I'm not even going to write out what psi n is because I don't have to. Because the way that we're going to be doing this is with the definitions of the position and momentum operators written uh, as combinations of the ladder operators. So h bar over 2m omega um, times the square root of that stuff, times the sum of the raising and lowering operators gives you x, the position operator, and then the uh, momentum operator is given by, why don't I have that written down somewhere? There it is. It's I times the square root of h bar m omega over 2 times the raising operator minus the lowering operator, right? And to do this, we're going to be making use of a couple of different rules. Um, those being that all of the wave functions are orthogonal to each other. So if you take the integral over all space of any one wave function with any other wave function, you'll get a Kronecker delta mn. I'm also going to make use of the fact that if you act the raising operator on a state psi n, you get root n plus 1 times psi n plus 1. And if you do the same with a lowering operator on psi n, you just get root n times psi n minus 1. So that's how we're doing this, right? So the expectation value of position for any given wave function psi n will be, of course, integral over all space of the complex conjugate of psi n times the position operator times psi n. So here we have, with the prefactor of h bar over 2m omega, inserting the ladder operators instead of the position operator, we have that this is now a plus plus a minus acting on psi n, right? And so distributing the wave functions into there, we can split up the integral into a psi n star times root n plus 1 psi n plus 1 and a psi n star times root n psi n minus 1. So just evaluating those integrals using the orthogonality condition, we have a Kronecker delta n plus 1 times the square root of n plus 1 and a Kronecker delta n minus 1 times the square root of n, right? And so both of those Kronecker deltas are 0 because Kronecker delta is defined as being 0 if m is not equal to n and 1 if m equals n. So both of these go to 0, and so for any wave function in the quantum harmonic oscillator, the expectation value of x is 0. So that's lovely. Similarly, we can just use a bit of Iron-Fest theorem to surmise that the expectation value of momentum for any of these states is also 0. So that is really cool. For x squared and p squared, though, we have different stories. So x squared of general wave function n, which is going to be psi n star x squared psi n dx. We have to expand x into the cool definition where the radical gets squared, so we have an overall factor of h bar over 2m omega, integral over all space psi n star a plus a minus squared dx, or actually psi n dx. And we'll expand the square. Right? So we'll have the squared raising operator plus the squared lowering operator plus the a plus a minus plus the a minus a plus acting on psi n. And that's what we're integrating. So, I mean, let's just do it all out. I don't want to confuse people. Even though it might take me a lot longer. Psi n star, we're going to act the raising operator on psi n twice first. So we'll get a factor of n plus 1 and also a factor of n plus 2 acting on psi n and integrating overall space. Or actually, this isn't psi n anymore. This is psi n plus 2 because we acted with the raising operator 2 times. Right? So that's that piece. We have acting the lowering operator on it twice. So we have a square root of n times n minus 1 on psi n minus 2 now dx. The other two terms are both tricky in comparison, and so I'm only going to act the one operator at a time. So first, that third term is going to act the lowering operator on psi n, which gives you a factor of root n times n minus 1. And then the fourth term acts the raising operator on psi n, so we'll have a factor of root n plus 1. And actually, this thing still has to act the raising operator on this, and the lowering operator is acting on psi n plus 1 now. Right? And all of that is being integrated from minus infinity to infinity. I don't know why I wrote it like that. Similar to what we did for the expectation value of x, we now have an integral of psi n times psi n plus 2. N is definitely not equal to n plus 2, or n minus 2 for that matter. So both of these integrals are 0. They won't contribute to the final answer. But in here we have a root n, and now acting the raising operator on psi n minus 1, we'll get another factor of root n times the integral of psi n with itself, plus a couple of factors of n plus 1 times the integral of psi n with itself. Those Kronecker deltas end up being 1. So squaring the square root of n will have n, and we'll also have n plus 1 from the other term. So both of those integrals were 1. So we have h bar over 2m omega times 2n plus 1, and I'll write it like that. Cool. We can look at the expectation value of momentum in much the same way. We'll have the minus infinity to positive infinity psi n p squared, that has a star on it, psi n dx. And then the momentum operator got expanded like this in terms of the raising and lowering operators. So I'm going to go ahead and actually move that down so I can look at it. Just going to set it there. That's the definition of the momentum operator in terms of ladder operators. Squaring it, you'll get a minus sign. So you have minus h bar m omega over 2. Right. And then we'll have in the integral now the square of the raising operator minus the lowering operator. And we can expand the square like this. We'll end up with the raising operator squared plus the lowering operator squared minus a plus a minus a plus, right? And we already did all of this at this point. We'll factor out a minus sign to make it a little bit more clear, and also just going to go ahead and get rid of these a plus squared and a minus squared because we know those go to 0. We'll have the integral of psi n star psi n dx with a square root n squared. I think that is the third term in there. It doesn't really matter. And then also a psi n star psi n dx root n plus 1 squared from minus infinity to infinity. Both of those integrals are 1 again. And so we just have n plus 1, which is 2n plus 1. So if we can use this now. Remember how in the last problem we were able to get a couple of different forms for the potential and kinetic energies using Iron-Fest's theorem, and then use that to verify the energy levels. This is 1 over 2m. We can do the same thing here. So the expectation value of any particular state n is going to be m omega squared over 2 times h bar over 2m omega 2n plus 1, and then the m cancels out, the omega cancels out. We'll have h bar omega over 4 times 2n plus 1. Similarly, for the kinetic, we'll have 1 over 2m h bar m omega over 2, 2n plus 1. The m's cancel out, so you get h bar omega over 4, 2n plus 1. They're the same, and that is normal. But then we can add them together to find the energy of any particular state En as being h bar over 2 times 2n plus 1. That is Tn plus Vn. Better specify that. And then factor the 1/2 through to get n plus a half, and now it looks like what Griffiths wrote. Anyway, pretty cool. We can also look at the uncertainty principle for any particular state n by multiplying together our values. So we have that the expectation value of x squared was h bar over 2m omega times 2n plus 1. And then for p squared, it was h bar omega over times m over 2 times 2n plus 1 again. And then the omegas and the m's cancel out, thank goodness. And you just get h bar over 2 times 2n plus 1, or if you like, h bar n plus a half. And it'll give you the uncertainty for any given wave function of the harmonic oscillator. All right.